Right now, while you are reading these words, something is happening that almost nobody on Earth knows about. A machine the size of a small car is moving through a part of the universe where no human being has ever looked, no probe has ever gone before, and no scientific model has ever been able to correctly predict what exists there. It is not a new spacecraft. It is not a product of modern engineering. It was built before the internet existed, before home computers existed, before most of the scientists currently studying its data were even born. It runs on roughly 4 watts of power. To put that in perspective, the small light inside your refrigerator uses more electricity than that. And this machine, this ancient, tiny, underpowered machine that was only ever supposed to last 5 years, is right now sending us information about the universe that is shaking the foundations of modern physics. The researchers who study its data are not using words like interesting or unexpected. They are using words like astonishing, baffling, and we were wrong. This is the story of Voyager 1. And here's the part the headlines are not telling you. It is not just what Voyager 1 found out there that should keep you up at night. It is what it found out there that directly affects the survival of life, right here on Earth. It is what is happening to it right now in 2026, that nobody is talking about. And it is what is going to happen in a few months, a date already locked into the calendar that will mark a moment no human civilization has ever reached before. Stay with me, because by the time this is over, you will never think about the night sky the same way again. I am your name, and this is your channel. Subscribe now if you want more stories like this, because we are just getting started. Let's go back to the beginning. September 5th, 1977. A rocket lifts off from Kennedy Space Center in Florida carrying a spacecraft called Voyager 1. The mission brief is simple and modest. Swing past Jupiter, swing past Saturn, take some photographs, collect some measurements, and then drift away into space and go quiet. The expected lifespan is 4 years, maybe 5. NASA plans to celebrate the mission's end sometime around 1981 or 1982. It would be a successful little trip, a nice postcard from the outer solar system, and then silence. What actually happened is one of the most extraordinary things in the history of science, and most people have no idea how extraordinary it actually is. Voyager 1 did not go quiet. It passed Jupiter in March of 1979 and sent back the first close-up images of that planet's surface that human eyes had ever seen. It passed Saturn in November of 1980 and kept going, accelerating as it went, using the gravitational pull of each planet like a slingshot to add more speed, more distance, more territory covered. By the time the 1980s ended, Voyager 1 had already traveled farther from Earth than any object humans had ever sent into space. And it was still transmitting, still sending its thin signal across the growing void, still collecting data, still functioning on hardware that modern engineers look at and shake their heads at in disbelief. Then in 2012, 35 years after it launched, something happened that made the entire story suddenly much bigger. Voyager 1 crossed the heliopause. If you have never heard that word before, it is the single most important boundary in our entire cosmic neighborhood, and crossing it is the equivalent of stepping out of everything our civilization has ever called home. Here is how to picture it. The sun does not just provide heat and light. It constantly releases a stream of charged particles called the solar wind, and this wind blows outward in every direction, pushing against the surrounding space and forming a giant protective bubble around our entire solar system. That bubble contains every planet, every moon, every asteroid, every comet, every spacecraft we have ever launched, and every living thing that has ever existed. The outer edge of that bubble, the point where the solar wind finally runs out of energy and gets stopped by the pressure of interstellar space pressing inward from the other side, that edge is called the heliopause. It is the actual physical boundary of our solar system. Everything inside it is ours. Everything outside it is something else entirely. And in 2012, Voyager 1 crossed through that boundary and came out the other side. It became the first object in human history to leave the solar system. Not a metaphor, not a technicality, the first physical thing our civilization has ever sent into the actual space between stars. And then it kept transmitting. Think about what that means. We have, right now, a live instrument sitting in interstellar space, not orbiting a planet, not floating in the outer solar system, not near the heliopause, actually inside the dark, cold, ancient space that lies between star systems. A space that no scientist, no telescope, no model built from the ground has ever been able to directly observe from the inside. And it is sending us data about what that space is actually like. And what it is telling us is not what anyone expected. Here is where the first twist in this story arrives. For decades before Voyager 1 got there, scientists had built detailed mathematical models describing what interstellar space should look like. Not guesses. Serious, peer-reviewed, rigorously tested models built by some of the smartest physicists alive. And those models all told roughly the same story. Interstellar space, the plasma between the stars, should be relatively quiet, relatively smooth. A thin, cold, sparse environment where particles drift slowly and not much happens. A kind of cosmic waiting room between star systems. Voyager 1 walked into that waiting room and found it was actually a storm. Starting in 2017, the plasma wave instrument on board Voyager 1 began detecting something that nobody expected and nobody could immediately explain. A persistent narrow band emission. A kind of faint but constant hum in the fabric of interstellar plasma that, according to every model built to describe this environment, simply should not be there in the way it is. Not a one-time burst, not a spike in the data that could be dismissed as a glitch. A continuous signal, year after year, stretching across a distance of over 900 million miles of interstellar space. To put that in perspective, the distance from the Earth to the Sun is 93 million miles. This emission has been detected across a stretch of space 10 times longer than the distance between our planet and our star. Scientists studying the data, published in the peer-reviewed journal Nature Astronomy, were clear in their conclusion. Interstellar space is not the quiet, uniform void that models described. It is turbulent. It has structure at every scale, from distances measurable in meters all the way up to distances measured in millions of miles. It is, in a physical sense, alive with motion and complexity that was completely invisible to us because we had never had a single instrument inside it before. Now stop and sit with that for a second. Every model built to describe our universe beyond the solar system was built from the outside looking in, from a planet, using telescopes and mathematics and theory. And now the first instrument we have ever actually put inside interstellar space is telling us that those models were missing something fundamental. That the universe beyond our solar system is more complex, more dynamic, more structured than we knew. But here is the part of this that stops being abstract and starts being personal, because those discoveries about interstellar space do not stay out there. They reach back here. The same bubble that separates our solar system from this turbulent interstellar environment is the bubble that protects life on Earth. The heliopause is not just a boundary line on a scientific diagram. It is a shield. It deflects the most dangerous forms of cosmic radiation, the high energy particles that stream in from distant exploded stars, from reaching the inner solar system at full strength. If that shield were significantly weaker or more unpredictable than our models suggest, the implications for biology on Earth would be enormous. And what Voyager 1 is telling us is that the interstellar environment pressing against that shield from the outside is more turbulent, more variable, and more energetic than any model has accounted for. We do not yet know exactly what that means for the long-term stability of the shield itself. But the fact that we now need to ask the question at all is itself a shift in how we understand our own vulnerability as a species. And now the story gets stranger. Because before we get to what Voyager 1 found at the boundary itself, we need to talk about what happened in 2023. Because in 2023, Voyager 1 nearly died. For 5 months, the spacecraft continued to transmit a signal back to Earth. But what it was transmitting was gibberish, corrupted code, scrambled data that the engineers at NASA's Jet Propulsion Laboratory, after decades of experience reading everything the spacecraft had ever sent, could not decode. The instrument was still alive. The signal was still coming. But whatever it was trying to say had become unreadable. For a team that had been successfully operating this mission since 1977, this was unlike anything they had ever faced. The cause, when they finally identified it, was both simple and devastating. A single memory chip inside the spacecraft's flight data system had physically deteriorated after nearly 5 decades of constant exposure to cosmic radiation. One small piece of 1970s hardware, one chip measuring a fraction of an inch, had developed a fault that was corrupting the section of software responsible for formatting and transmitting scientific data. No alarm had gone off. No warning had been sent. The chip had just quietly failed after 46 years of nonstop operation in the harshest environment a human-made object has ever been placed in. In any normal engineering situation, you fix a broken component by going to where the component is and replacing it. In this situation, the component was 15 billion miles away, unreachable by any known form of transportation, with no repair mission possible in any time frame that would matter. The only available tools were radio signals traveling at the speed of light, and even those signals took 22 hours one way to reach the spacecraft. 22 hours just for the message to arrive, another 22 hours for any response to come back. Every single diagnostic step, every attempt to probe the problem, every test of a potential solution required a minimum wait of 44 hours to complete a single round of communication. Think about what that engineering process actually looked like from inside the control room. You look at a piece of data, you form a theory about what might be wrong. You write a set of instructions designed to test that theory. You transmit those instructions. You wait 22 hours. You receive whatever the spacecraft sends back. You analyze the response. You discover something slightly different from what you expected. You form a new theory. You write new instructions. You transmit them. You wait 22 hours again. You continue this process step by patient step for months. And every single moment of that process carries the knowledge that a single wrong instruction, sent once across 15 billion miles of void, could permanently end the mission with no recovery possible. The team at JPL worked through this for months, carefully, methodically, under a kind of pressure that most engineering situations never produce. And they succeeded. They figured out that the corrupted code could not be repaired, but it could be relocated. The affected portion of software was split into smaller sections and stored in different places in the spacecraft's available memory. Each section individually checked and rewritten to work correctly from its new location, then carefully reconnected to function as a whole. It was, in effect, brain surgery performed remotely through a 44-hour time delay on a machine nearly 50 years old sitting 15 billion miles away. In mid-2224, Voyager 1 came back online and began transmitting clean, readable, complete scientific data again. And what it immediately resumed sending back was more evidence of those persistent, unexplained plasma oscillations in interstellar space. More measurements of the turbulent structure that the models had never predicted. The spacecraft that should have died in 1981 had come back from what could have been its final silence, and it came back with more things to tell us. But none of that, not the discovery, not the near death, not the recovery, prepared anyone for what Voyager 1 had actually found at the moment it crossed the heliopause back in 2012. Because this is the part of the story that the scientific papers describe in language that stops feeling like physics and starts feeling like something else entirely. For decades, the models describing the heliopause, the outer edge of our solar system, predicted what crossing it should feel like to an instrument moving through it. The solar wind on the inside gradually thinning out, the interstellar medium on the outside gradually becoming detectable. A slow, smooth transition from one environment to the other, a gradual blending at the edges, like the place where a river slowly meets the sea. That is not what Voyager 1 found. At the heliopause, the particles were not thinning out calmly. They were moving at speeds approaching a significant fraction of the speed of light. They were slamming into each other at energies that generated temperatures approaching 30,000 degrees Celsius. Not in the sun, not in any star, but at the outer edge of our own solar system, in what was supposed to be relatively cold, sparse transitional space. Some researchers have described this region as a wall of fire. And not fire as a metaphor, a genuine concentration of ultra-energetic charged particles forming a physical barrier at the boundary of everything we call home. And then the magnetic discovery. For decades, one of the foundational predictions about crossing the heliopause was that the magnetic field environment would change dramatically. Inside the bubble, the sun's magnetic field. Outside the bubble, the completely separate magnetic field of the galaxy. Two distinct environments with distinct magnetic personalities, separated cleanly at the boundary. Voyager 1 found something completely different. The magnetic fields on both sides of the heliopause were, in ways that existing theory had not predicted, connected. The sun's magnetic field lines, carried outward by the solar wind and compressed at the boundary, were interacting with the galactic magnetic field outside, in a process called magnetic reconnection, where field lines from different sources rearrange themselves and release energy in the process. The solar system and the galaxy surrounding it are not magnetically separate. They are magnetically linked. At the boundary between everything we know and everything we have not yet explored, there is a zone where energy is being exchanged between our home and the wider cosmos in ways that every model built before Voyager 1 crossed that boundary had simply not accounted for. This is not a footnote. This is not a minor correction to existing theory. If the relationship between the solar system and the interstellar environment is more dynamic, more connected, and more energetic than the models described, then our understanding of how the heliosphere protects Earth over geological timescales needs to be reconsidered from the beginning. Now let's talk about what is happening right now in 2026, because the story is not over. It is, in fact, entering what may be its final chapter, and the timeline is tighter than most people realize. Earlier this year, NASA made a decision that nobody inside the mission wanted to make. The low-energy charged particle experiment, one of Voyager 1's scientific instruments that had been collecting data almost without interruption since the spacecraft launched in 1977, was switched off, not because it stopped working. It was still working fine. It was shut off because Voyager 1 is running out of power and there was no longer enough to keep it running. Voyager 1 gets its power from three devices called radioisotope thermoelectric generators. These are essentially containers of plutonium-238 that produce heat as the plutonium slowly decays, and that heat is converted into electricity. At launch, these generators produced around 470 watts of power. Today, nearly 49 years later, they produce roughly 250 watts. They lose about 4 watts every year. At some point in the early 2030s, the output will fall below the minimum level needed to run any remaining instrument at all, and Voyager 1 will go permanently silent. The team managing the spacecraft has known this was coming for years. Years ago, the scientists and engineers sat together and worked out a careful plan for which instruments to shut off, and in what order, to squeeze as much scientific value as possible out of the dwindling power supply for as long as possible. Of the 10 scientific instrument packages Voyager 1 carried when it launched, 7 have already been turned off. The decisions about what to turn off and when are some of the hardest choices a scientific team ever has to make, because each instrument lost is a set of questions that will never be answered, and because there is no way to turn an instrument back on if you later decide you switched it off too early. But here's the twist that almost nobody outside the JPL mission team is talking about. They have not given up on getting more time. NASA engineers are currently working on something they have reportedly referred to internally as the Big Bang procedure. It is an experimental attempt to restructure how power is distributed across Voyager 1's remaining systems in order to extract additional electrical capacity from components that are currently operating at lower efficiency than they could be. The idea is technically complex and carries real risk because even small changes to how power flows through a nearly 50-year-old spacecraft with no manual override available could cause unpredictable results. So the team is doing what careful engineers do. They are testing the procedure first on Voyager 2, which carries slightly more available power and is somewhat closer to Earth, making a potential failure slightly less catastrophic. Tests on Voyager 2 were scheduled for May and June of 2026. If those tests show the procedure is safe and effective, the same approach will be attempted on Voyager 1, with the earliest possible attempt scheduled for no earlier than July of this year. And here is the detail that makes that significant. If the procedure works, there's a real possibility that the low-energy charged particle instrument, the one that was just shut down, could be switched back on. The team is cautious. They are not making promises, but they are still trying. Because with Voyager 1, the history of assuming things were finished before they actually were has never once aged well. And now comes the moment on the calendar, the one that is already locked in, already certain, the one that no human civilization has ever reached before and that will arrive regardless of whether anyone is paying attention to it. On November 18th, 2026, at 16 minutes and 12 seconds past 2 in the morning Pacific Standard Time, Voyager 1 will reach a distance of exactly 1 light day from Earth. That means it will be so far away that a signal moving at the speed of light, the fastest anything in the universe can travel, will take exactly 24 hours just to reach it. If you send a command to Voyager 1 on a Monday morning, you will not know if it arrived until Tuesday morning, and you will not receive the spacecraft's response until Wednesday morning. 2 full days of waiting just to complete a single exchange of information. No human-made object has ever been that far from Earth, not once in the entire history of civilization. And on that date in November 2026, Voyager 1 will cross that threshold for the first time, while it is still alive, still transmitting, still sending back data, and then it will keep going. Every hour, it travels roughly another 38,000 miles deeper into interstellar space. The communication delay will keep growing, the power supply will keep shrinking. And at some point in the 2030s, the last signal will come. But even when that happens, Voyager 1 does not stop. There is nothing in interstellar space to stop it. No friction, no atmosphere, no gravity strong enough to pull it off course significantly. It will just keep moving silently in a straight line at 38,000 miles per hour into darkness that has no end on any human timescale. And bolted to its frame, attached to the body of this dying machine, is something that will outlast all of it: the Voyager Golden Record. A gold-coated copper disc carrying greetings spoken in 55 human languages, the sound of rain falling on a forest, the sound of ocean waves, the sound of human laughter, 90 minutes of music chosen from cultures across the entire history of human civilization, diagrams explaining the basic principles of our physics and mathematics, and a map made from the positions of pulsars designed to show whoever finds it exactly where in the galaxy our planet sits. Carl Sagan, who helped design the record, described it as a message in a bottle cast into the cosmic ocean, and that is exactly what it is. Because whoever or whatever eventually finds it, whether that is another civilization, 1,000,000 years from now, or some form of intelligence we cannot currently imagine, the record will tell them something true. That there was a species here, that they were curious, that they reached, that they built a machine from metal and electricity and mathematics, and launched it beyond everything they had ever known, carrying the sound of their own laughter. The record will still be traveling when the sun has become a red giant and swallowed the orbit of the Earth. It will still be traveling after every human city and every human archive, and every piece of stone we ever carved our names into has been erased by geology and time. It is the most permanent thing our civilization has ever made, and it is riding on a spacecraft that currently runs on less power than the light above your bathroom sink. Now come back to the science, because there is one more thing Voyager 1 is doing right now that deserves to sit at the center of this story. The persistent plasma emission it has been detecting since 2017 is not just an anomaly. It is, according to the researchers analyzing it, the first continuous real-time measurement of interstellar plasma density that humanity has ever obtained. Before Voyager 1 started detecting this emission, scientists could only take isolated snapshots of plasma density in interstellar space. Measurements triggered by specific events like shocks produced when giant eruptions from the sun traveled all the way out to the heliopause and sent ripples into the interstellar medium. Those measurements were valuable but scattered, like trying to understand what the weather is like across a whole continent by checking a single thermometer once a year in one city. What the persistent emission from Voyager 1 is providing instead is something closer to a continuous feed, a running portrait of interstellar plasma as the spacecraft moves through it, day after day, year after year. And what that portrait is showing us is that interstellar space is not a static, uniform background. It has texture, it has weather, it has structures built from charged particles and magnetic fields that stretch for millions of miles and interact with the outer boundary of our solar system in ways that models built from Earth could not detect or predict. The space between stars is not empty. It is full, it is active, it has a physical personality that we are only now, for the first time in human history, beginning to actually read. There is a question at the center of all of this that the scientific community has not yet been able to answer. The persistent emission has two possible physical explanations, and researchers working on Voyager 1 data have not yet been able to determine which one is correct. The first possibility is that the emission comes from thermally excited plasma oscillations, the natural vibration of plasma particles interacting with their surroundings. This would be a genuinely significant discovery, but it would fit inside existing physical frameworks without requiring them to be rebuilt. The second possibility is that what Voyager 1 is detecting is something called quasi-thermal noise, a different physical mechanism that carries information about plasma density and temperature in a subtly but importantly different way, one that would require existing models of the interstellar medium to be substantially revised. Distinguishing between these two explanations requires either additional data from Voyager 1 itself, which is producing less of it every year as more instruments are shut down, or a new mission specifically designed to study interstellar space with instruments built for exactly this purpose and capable of making the measurements needed to settle the question. No such mission currently exists. No such mission is currently funded. The next spacecraft capable of reaching interstellar space and crossing the heliopause, if it were funded and built and launched today, would not arrive at that boundary for at least 25 years. Which means that when Voyager 1 finally goes silent, the question it raised will still be open. The map it started drawing will stop being updated, and the only real-time window into interstellar space that our civilization has ever opened will close and stay closed for decades. That silence is coming. The date is not fixed yet, but the direction is. Every year the power drops. Every year more instruments go offline. Every year the team at JPL makes harder choices about what to keep running and what to let go. And somewhere in the early 2030s, the last instrument will reach the minimum power threshold, and the last signal will begin its 24-hour journey home and arrive and be recorded, and there will be nothing after it. After that, Voyager 1 will just keep moving, silently, at 38,000 miles per hour, carrying its golden record through the darkness, passing through regions of the galaxy that human eyes will not reach for tens of thousands of years, continuing the journey that began on a morning in September 1977, when a group of engineers pointed a machine at the stars and pressed the launch button expecting it to last 5 years. Here is what I want you to take away from all of this, because there's a fact sitting in the middle of this story that is easy to miss when you are focused on the discoveries and the physics and the engineering. Right now, in 2026, the only live scientific instrument that humanity has ever placed in interstellar space is 48 years old. It was built using technology that predates personal computers. It is powered by less electricity than the light above your kitchen stove. And it is sending back information that is changing how we understand the universe and our place inside it. We have built things that are much larger. We have built things that are much more powerful. We have built things that cost far more money and involve far more complex technology. And none of those things have told us what Voyager 1 is telling us right now. Because none of those things had the one thing that Voyager 1 had. None of them had the audacity to keep going long enough to actually get there. There are questions about the universe that can only be answered from inside the universe, not from a telescope on the ground, not from a satellite in Earth orbit, not from a mission to Mars or the asteroid belt, only from a machine that crossed the heliopause and entered the space between stars. We have exactly one such machine. It is old and dying and running on 4 watts of power. And as long as it is still transmitting, we need to be listening. Because when it goes quiet, the answer to some of the most important questions we have ever asked will go quiet with it, at least for a generation. The signal is still coming, stretched across 15 billion miles, delayed by 22 hours of travel time, carrying information about a universe that is stranger, more turbulent, more connected, and more extraordinary than any model built from Earth had ever correctly described. One machine, 4 watts, one chance to listen. The question is whether anyone is paying attention. If this kind of story is what you come here for, subscribe right now and turn on notifications. Because we are going deeper into the edges of what science actually knows next time. Drop a comment with what surprised you most in this video. And share this with someone who needs to hear it, because this story deserves more than the silence it is getting. Thanks for watching.